Hi everyone, so in this video we'll introduce some additional notation in logic for quantifiers, and we'll see how we can use these quantifiers to express English sentences and how we can express English sentences in symbolic logic. And so it's going to be helpful to take an English sentence, rewrite it using symbolic logic, and that will help us understand the logical structure, and that will be a good first step in trying to prove whether or not that sentence is true or false. So the first symbol is this upside down A, and that quantifier, this upside down A, is used to denote for all, and we call this the universal quantifier. The other quantifier is this backwards E, and we use the E to represent there exists, and therefore we call this the existential quantifier. And though it's not a quantifier, I'm not sure if everybody is familiar with this symbol, so I just want to define it here, that this symbol that looks like an E almost denotes the in. So let's take a look at what an example for this. So for example, if we see in symbolic logic representation this backwards E, X in Z, in English, we could write this out as there exists an integer X. So this weird looking Z, recall, is used to denote all integers. So there exists an X in Z. That means there exists an integer. Okay, so let's try and take a look at some statements similar to this one and see how we can translate something from symbolic logic into English. Okay, so here we have 4 statements expressed mostly using symbolic logic. And we have quantifiers, sometimes multiple quantifiers in these statements. So let's take a look at each of these and see how we could express them in a more intelligible, say, English sentence. So for the first sentence, we have a couple of parts here. So first of all, we've got for all X in U, where U is all people. And then we've got a second part of this sentence, which is X loves Raymond. And let's see how we could interpret this. So if we parse it, each of these two pieces, the part highlighted in red is saying for every person in U, which is the world. So for every person in the world, then we can translate the blue part, X loves Raymond. X is just representing each person now. So we could say for every person in the world, each person loves Raymond. And there are often many different ways, just like when you're writing things in English, when you're writing papers, there are very different ways that we could express the same thought. And so something that you might want to keep in mind now is that certainly finding the most elegant way to express yourself is preferred. So this statement is correct. Maybe it's not the clearest way of stating it. And instead, if we were to say everyone loves Raymond, that is logically equivalent to the previous sentence. And that is a more elegant way of stating that. Okay, so next up is number 2. And so here, let's break this down again into components. So we have for all X in R, that's how we would read that in English. There exists Y in R, so that Y cubed is equal to X. And let's see how we could interpret this. And again, we can do this bit by bit. So the red part is telling us for every real number X, there exists a real number Y such that Y cubed is equal to X. And while we're thinking about this statement, let's think about whether this statement is true or false. So given any number X, can we find the Y such that X is equal to Y cubed? Yes, we certainly can. We could pick Y equal to the cube root of X. Okay, so given any X, we can certainly find a real number y such that y cubed is x. We just would set y equal to the cube root of the value x. So this is a statement, and this is actually a true statement. And now let's compare the example in 3. And so notice what happened in 3. We have flipped the order of these two quantifiers. So now first comes there exists a y in R. So first we've got this piece coming first. So for all x in R, we have y cubed is equal to x. And so first, let's translate this into English, and then we can think about whether this statement, when we flip the order of these two quantifiers, whether that affects the truthness of this statement or not. So we could interpret this, first of all, in English by saying there is a real number y with the property that y cubed is equal to x for every real number x. And so this is a totally ridiculous statement here. This is definitely a false statement when we flip the order around. There's no number y that this would hold for every single value of x. So when we change the order around, that definitely changes the meaning of that logical statement, and that might affect whether or not that statement is true or false. Okay, and for the last one, here we've got for all x in n, and this n over here is denoting the set of natural numbers, 1, 2, 3, 4, 5, 6, so on. We're told that if x is even, so remember this symbol over here is the conditional symbol that we use to denote if then. And then what comes after this symbol is what's called the conclusion of this conditional, and that is a disjunction. So here the conclusion, we would say if x is even, then either x is equal to 2 or x is a composite number. So altogether, we've got for every natural number x, if x is even, then either x is equal to 2 or x is composite. And I should just say over here that when we say composite, what we mean is that it can be written as a product of two numbers that are less. And again, natural numbers, these are 1, 2, 3, 4, 5, 6, integers greater than or equal to 1. And so maybe we can state this a little bit more elegantly. I'll give that a shot over here. So this would be equivalent, logically equivalent to saying every even natural number x is either equal to 2 or it is composite. And if you're curious about whether this one is true or false, this is a true statement. But really here the point is to practice taking symbolic logic and being able to interpret it in terms of English. And on the last slide, I want to do the reverse of this process, which is take English sentences and express them using symbolic logic. Okay, so now let's practice taking something in English and writing it in terms of symbolic logic. So this is often the way that we're going to start proofs. We have a statement written in English. We want to determine whether that statement is true or false. Let's interpret it into symbolic logic, and that will help give us some of the logical structure of that statement. So the first sentence here is, if x is a positive real number, then x over 2 is a positive real number. So we've got a conditional here, and the hypothesis is if x is a positive real number, I'll highlight that in blue, and the conclusion is then x over 2 is a positive real number. So let's just translate each of those, and because we have a conditional statement, we would want to use the arrow indicating conditional. So I could write this, if x is bigger than 0, then x over 2 is bigger than 0. So that would be one way that we can write the conditional statement. And now that I have it in this form, we can think about whether this statement logically is true or false. If x is positive, then when we divide it by 2, it's still going to be a positive number. So this is indeed a true statement. And when we are proving and interpreting implications, conditional statements like this, really what we're saying is that this is true for every value of x bigger than 0. So these conditional statements are really for all statements in disguise. And so when we're reading these conditional statements, it really should be understood as a for all statement. And so that we would usually put a for all x in R to mean for all real numbers x. If x is positive, then x over 2 is positive. So this quantifier, this universal quantifier, it's good to get in the habit of placing that before any of these conditional statements. In number 2, the statement is every differentiable function is continuous. And so first, we might want to just restate this in English terms and recognize that this is a conditional statement. Okay, so sometimes conditional statements might be in disguise and might not explicitly say if then. But what this statement is saying, this sentence is saying, is equivalent to saying if a function f is differentiable, then that would imply that function f is continuous. And so we have a conditional statement here. So we can state this as follows. So we could say f differentiable implies f continuous. That's fine, but remember, we want to make sure we put this universal quantifier in front of that. So what we mean here is for all functions f, if f is differentiable, then f is continuous. This is a true statement, in case you are curious. But that is how we could express that using symbolic notation. And then lastly, here's maybe a tricky one. Logically, we can see that this is indeed true. But how could we state this using symbolic logic? Let's first take this English sentence and start to move it in the direction where it would more naturally match up with our quantifiers. So for example, we could restate this in the following way. For any real number x, there exists a real number y such that y is less than or equal to x, right? Logically, that is saying the same thing as there is no smallest real number. And so now that we've got this written, and you can see we've got for any real number, there exists a real number, it's a little easier now to pair this up with a corresponding statement like this. So we've got for any real number, so we've got the universal quantifier for all x in the real numbers. There exists a number y, so now we would use the existential quantifier. There exists a real number, there exists a y in R with the property that y is less than or equal to x. Okay, so we will practice more of this in class, give the quiz a shot, and see everybody on Zoom.